Introduction. I-beam are renowned for their strength to weight ratio, designed with flanks and webs to handle bending and shear stress effectively, critical for application in building, bridge, and industrial frame. Stress analysis ensure reliability under various loads. 1.1 I-beam structure in aircraft design. Balance weight and strength for optimal performance and safety. Used in wing, fuselage, section and floor support. Material like titanium, steel, and aluminum for dynamic loading. Essential for fuel efficiency and reduce operating costs. Manage comprehensive tensile and shear force effective. Finite element method (FEM) in stress analysis. FEM break I-beam into finite element for precise analysis. Simulate real-world scenario, take-off flight, and landing. Tools: CATIA for stress and deformation analysis. FEM in aircraft application evaluate combined loads, vibration, thermal expansion, aerodynamic forces. Optimize material use and ensure safety compliance diagram given result of analysis for material steel on aircraft I-beam. Objective: creating a finite element model of a crucial aircraft structure I-beam, examining shear and bending stress under different load scenarios such as dynamic flying load, examining how performance is affected by grammatical change and material characteristics.
The analysis began with the creation of I-beam model in CATIA, a powerful design and simulation tool widely used in engineering. The geometry of I-beam was carefully defined to match structural requirements typical of aircraft application. Key dimensions included a flange width of 50 mm, a flange thickness of 10 mm, a web height of 100 mm, and a web thickness of 5 mm. These dimensions were chosen based on their relevance to load distribution and weight optimization in aerospace structures. Material properties were assigned to the I-beam with the isotropic characteristics, ensuring uniformity in mechanical behavior across all directions. Specific values for Young's modulus, Poisson's ratios, and density were applied all the material. For instance, stainless steel was assigned for a Young modulus of 210 gigapascal and a Poisson's ratio of 0.3 and density of 7,850 kg per m cube. Carbon fiber, known for lightweight and properties, had Young modulus of 70 gigapascal, a Poisson's ratio of 0.3 and density of 1,600 kg per cube. Titanium, reorganized for its exceptional strength, was assigned for a Young modulus of 110 gigapascal and a Poisson's ratio of 0.3 and density of 4,500 kg per m cube. These properties were essential for accurately simulating the material's behavior under various loads. To simulate real-world conditions, boundary conditions were applied to the I-beam model. Fixed supports were established on one end of the beam to represent typical constraints in aircraft structures. Operational forces were then applied to replicate realistic loading scenarios. A bending force of 10,000 Newton was introduced to evaluate the beam's performance under the flexural stress. Additionally, a shear force of 5,000 Newton and torsional movement of 1,000 Newton were applied to simulate the combined loading conditions after encountered during the flight, landing or takeoff. CATIA's advanced simulation tools were utilized to analyze the stress distribution, deformation patterns, and critical failure points of the I-beam. The analysis included generating a detailed finite element mesh, ensuring a high level of precision in capturing stress variation. A mesh convergence study was conducted to optimize the balance between the computational efficiency and accuracy, confirming the mesh density was sufficient to provide the reliable results. The study involved a comparison of these materials, which is stainless steel, carbon fiber, and titanium. Stainless steel with the yield strength of 250 MPa was included for the high strength but noted to the heaviest material analyzed. Carbon fiber with the yield strength of 450 offered exceptional weight efficiency, achieving a strength to weight ratio of 281,250 Newton per kg. This was made it strong contender for application when minimizing weight in priority. But titanium with the yield strength of 950 MPa stood out as the strongest material, making it ideal for the high load application. Its combination of yield strength and moderate density provided a balanced solution for components subjected to extreme forces. The simulation revealed detailed insights into the performance of each materials under the applied loads, stress distribution maps, and deformation patterns highlighted critical regions within the I-beam, such as areas near the support and midspan, where the maximum stress and the deflection occurred. These results were instrumental in understanding how each material performed under the identical conditions and provided a basic comparing their suitability for aerospace application. By integrating precise modeling, realistic boundaries conditions, and material-specific properties, this methodology provided a comprehensive framework for evaluating I-beam performance. This approach ensured that the findings were not only accurate but also directly applicable to challenges of aircraft structural design.
Sketch I-beam in CATIA step by step. First, sketch I-beam, follow the dimension given. Pad width 500 mm. Select all the edge of the beam and choose fillet option to get fillet edge. Sketch I-beam in CATIA step by step. First, sketch I-beam, follow the dimension given. Pad width 500 mm. Select all the edge of the beam and choose fillet option to get fillet edge. Sketch I-beam in CATIA step by step. First, sketch I-beam, follow the dimension given. Pad width 500 mm. Select all the edge of the beam and choose fillet option to get fillet edge. Sketch I-beam in CATIA step by step. First, sketch I-beam, follow the dimension given. Pad width 500 mm. Select all the edge of the beam and choose fillet option to get fillet edge. Sketch I-beam in CATIA step by step. First, sketch I-beam, follow the dimension given. Pad width 500 mm. Select all the edge of the beam and choose fillet option to get fillet edge. Sketch I-beam in CATIA step by step. First, sketch I-beam, follow the dimension given. Pad width 500 mm. Select all the edge of the beam and choose fillet option to get fillet edge. Sketch I-beam in CATIA step by step. First, sketch I-beam, follow the dimension given. Pad width 500 mm. Select all the edge of the beam and choose fillet option to get fillet edge. Sketch I-beam in CATIA step by step. First, sketch I-beam, follow the dimension given. Pad width 500 mm. Select all the edge of the beam and choose fillet option to get fillet edge. Sketch I-beam in CATIA step by step. First, sketch I-beam, follow the dimension given. Pad width 500 mm. Select all the edge of the beam and choose fillet option to get fillet edge. Sketch I-beam in CATIA step by step. First, sketch I-beam, follow the dimension given. Pad width 500 mm. Select all the edge of the beam and choose Fillet option to get fillet edge. Sketch I-beam in CATIA step by step. First, sketch I-beam, follow the dimension given. Pad width 500 mm. Select all the edge of the beam and choose Fillet option to get fillet edge. Sketch I-beam in CATIA step by step. First, sketch I-beam, follow the dimension given. Pad width 500 mm. Select all the edge of the beam and choose Fillet option to get fillet edge. Sketch I-beam in CATIA step by step. First, go to selection material, choose steel, click it, and remember, for other material that we want to use, just pick it here, and after that click analysis and simulation, click at generative structural analysis. After that, click the clamp and choose on the both side of the I-beam. Select pressure and apply on the surface of I-beam. Apply 10 load, compute the data and stimulate. Go to selection material, choose steel, click it, and remember, for other material that we want to use, just pick it here, and after that click analysis and simulation, click at generative structural analysis. After that, click the clamp and choose on the both side of the I-beam. Select pressure and apply on the surface of I-beam. Apply 10 load, compute the data and stimulate. Go to selection material, choose steel, click it, and remember, for other material that we want to use, just pick it here, and after that click analysis and simulation, click at generative structural analysis. After that, click the clamp and choose on the both side of the I-beam. Select pressure and apply on the surface of I-beam. Apply 10 load, compute the data and stimulate. Go to selection material, choose steel, click it, and remember, for other material that we want to use, just pick it here, and after that click analysis and simulation,
Assalamualaikum warahmatullahi wabarakatuh. I will present about result and discussion. Okay, at this slide, the table is about the material properties, which is there are three material: stainless steel, titanium, and carbon fiber. Okay, first we go to the density. The higher density is stainless steel, and then titanium, then carbon fiber has the least density compared to other material. So due to the least density, carbon fiber is the lightweight and the stainless steel is the heavyweight. Okay, next we go to the yield strength, which is the unit is megapascal. Stainless steel has the lower yield strength and titanium has the bigger yield strength. Due to the bigger yield strength, titanium can support more weight compared to stainless steel and carbon fiber. Okay, next we go to the Young modulus. The bigger Young modulus is carbon fiber and then stainless steel. Then the least Young modulus value is titanium. Okay, then the last is Poisson ratio. The least Poisson ratio is stainless steel, and then is carbon fiber. Then the bigger Poisson ratio is titanium, which is the value is 0.34. Thank you.
I will be presenting a comparison of three materials. First, let's look at carbon fiber. The von Mises stress in carbon fiber ranges from 15.2 to 353 Nm², with visible stress concentration in areas where the model is clamped and where the load is applied. It experiences the highest amount of stress and deformation among the three materials due to its relatively low yield strength, make it more prone to deformation under the load. However, its low density provides a significant weight advantage, making it an excellent choice in lightweight structures under moderate load conditions. In summary, carbon fiber is ideal for application where weight reduction is a top priority. Next, we have titanium. The von Mises stress in titanium ranges from 15.1 to 355 Nm², with stress distribution patterns similar to aluminium. The titanium strikes a balance between lightweight and moderate strength, as it is stronger than aluminium but has a lower density compared to stainless steel. This makes it particularly suitable for applications requiring structures that are lightweight yet moderately strong. Titanium is a great compromise when both weight reduction and load carrying capacity are important. Now, let's discuss stainless steel. The von Mises stress in stainless steel is slightly higher, ranging from 15.1 to 376 Nm², with stress concentration observed at clamping points and load application areas. Due to its high yield strength, stainless steel exhibits the least amount of displacement and deformation, providing superior resistance to applied loads. However, it has a high density, making it the heaviest of the three materials. This trade-off makes stainless steel ideal for application where maximum strength is needed and weight is less of a concern. In conclusion, carbon fiber is the best option for lightweight application under moderate load conditions. Titanium offers a good balance between lightweight and moderate strength, making it versatile for many structural applications. Stainless steel is the material of choice for high load scenarios where maximum strength is essential and weight is not a major factor. So the choice of material ultimately depends on the specific demands of the application, including load conditions, weight requirement, and resistance to deformation. Thank you.
My name is Noyana Shahamti Saiful. I will explain about the conclusions. So for the conclusion, the analysis of stainless steel, titanium and carbon fiber highlight their strengths for different application. For the stainless steel, it's highly durable and resists deformations, make it built for heavy load scenario where weight is not a concern. However, in high density, make it heaviest option. Titanium strike a balance between strength and weight, make it suitable for moderate load in high weight structure. This offers excellent performance in aerospace and high performance application due to its lower density and strong long load carrying capacity. Carbon fiber stand out for its lightweight and high strength to weight ratio, make it perfect for application where reducing weight in is critical. However, it deforms more easily under high stress compared to other materials. In conclusion, the selection of the material is depend on the specific application requirement. As long as, for example, for titanium, it's the best for the scenario demanding a balance between weight and strength. Carbon fiber excel in high weight design with moderate load, and stainless steel is preferred for high load application where weight is less critical. This finding guide this optimization of material selection in aircraft structure to enhance performance